Today, our first speaker is Arindam Khan, who is a faculty member at IISc Bangalore. He will be continuing his talk on approximation algorithm for maximum independent set of rectangles. Thank you, Arindam.
Thank you, Arindam. And welcome everyone for today's talk. So yesterday we talked about some basic notions and definitions related to maximum independence of rectangles, and we started talking about the approximation algorithm. But today it will be more technical, and we'll go deep into the algorithm. But in the first 5 minutes, let me recapitulate what we did yesterday, and then we'll start. So yesterday we talked about first definition of approximation algorithm, and then we talked about petas, epetas, fpetas, qpetas, etc. So if you, I'll just go over quickly, but if you need any point to stop me, I can stop and explain if something is not clear, what I did yesterday. And then we talked about rectangles and packing problems, why they're cool, and then talked about independent set problem, then talked about geometric intersection graph, and talked about the algorithm for independent set of rectangles, maximum weighted independent set of intervals. And there we talked about a dynamic program algorithm, and we told that our algorithm will be a generalization of this idea only. And finally, this is the problem which we study. We are studying that we're given a set of n axis parallel input rectangles, and the goal is to find a set of non-overlapping rectangles of maximum cardinality. So in this example, this is a set of maximum cardinality non-overlapping rectangle. So you have both geometric viewpoint where you have non-overlapping rectangles, and the graphical viewpoint where if you create the geometric intersection graph of rectangles where there is an edge between two nodes if the objects overlap, and if you find the independent set in that particular graph, also giving you this non-overlapping set of rectangles. And then we showed why theoretically important connections with several other problems and the present state of approximability. And as we mentioned, the previous base was 10 approximation, and the goal was to get an improved approximation guarantee with better runtime and simpler analysis. So this was the slide which I talked. I spent some time yesterday, but let me go over this again. So what we are giving is we are giving a 2 plus epsilon approximation, and the idea is as follows: that there are too many number of candidate independent sets, exponential in number. So what we're looking for some kind of structured solution. So yesterday we talked about guillotine cuts. So guillotine separable solution will show it to be a structured solution. And one can show you can find the best guillotine separable solution in polynomial type. So the size of the space of all best guillotine separable solution, that's only a polynomial size subset. And then what we'll show that if there is a good approach, if we can show any guillotine separable set, any independent set, if I take, there is a good guillotine separable set which is within a small factor from the independent set, then using that property, we can actually find that solution by a DP, and that will return us some solution with some approximation guarantee. So we'll go over this idea in detail today, but that's a high level thing that we're doing, that we have a lot of candidate solution. We want to create some kind of structured space which we can find efficiently, which structure efficiently in polynomial time. And these structured solutions are good approximation of the original set of candidate solutions. And then also this is kind of the best that you can achieve, because presently even for line segment, axis parallel line segment, 2 approximation is best known and nothing is better. Nothing is known which is better than 2. This is the status. And then we talked about guillotine cuts yesterday. And guillotine cuts are end-to-end cut, which divides a piece into 2 rectangular pieces, and that creates some kind of a tree structure like this. We saw that we start with some object, some rectangular piece, and then we cut, and then you would get 2 pieces, and then again we cut and continue. So you're getting a binary tree, and at the end, each leaf contains exactly 1 rectangle. And the question was whether you can extract all rectangles. So a rectangle is not killed if it is finally, it belongs to some kind of a leaf node, and it does not intersect any of the guillotine cuts. So the question was, can you always separate out all the rectangles by guillotine cuts? The answer was no. but can you separate constant fraction of the rectangles? And that was a conjecture, but the best bound we know is there are some examples where you cannot separate out more than n by 2 rectangles. So half fraction you have to lose. But on the algorithmic side, the best we know is n by log n plus 1. So there's a huge gap. And then we talked about the algorithm, how you get this n by log n plus 1 rectangles. Basically, you create log n number of poles and you show each of, and you divide the set of rectangles into these log n classes, and you can show each of these classes you can separate using guillotine cuts. So if you take the highest weight class from them, you will already get n by log n plus 1 rectangles. So this was a state where we stopped. So now let me continue. But any question regarding previous yesterday's talk? Okay. So now we'll talk about the connection between guillotine cuts and MISR. So when we talk about MISR, we are given a set of rectangles which are overlapping. Whereas in guillotine cuts, we're talking about set of rectangles which are non-overlapping. So think of a MISR instance, which might be something like maybe something like this. Whereas for the guillotine separable instance, the object are something like this, which is non-overlapping. So how do we connect these two problems? So first, let's say we have this existential property that if I have any embedding of n non-overlapping rectangles, then there are n by alpha fraction of rectangles which can be separated by guillotine cuts. So it's an existential property. I don't need an algorithm, just some property, even if it takes exponential time, that's fine. Now assume the optimal MISR solution is opt. So maybe this is the MISR solution that I have, MISR instance, and this is the solution, opt of MISR. Now as you see, the optimal solution of MISR is a set of non-overlapping rectangles, but they may not be guillotine separable. But the conjecture, the property P1, it ensures that if it is true, then opt may not be guillotine separable. But if I start with the optimal solution, that is non-overlapping, so at least opt by alpha number of rectangles will be guillotine separable. And then we'll show that actually there is a dynamic program which returns the optimal guillotine separable set for a MISR instance in order n to the power 5 times. And okay, there is a question. Why is the guillotine cut problem only defined for non-overlapping rectangles? No, actually it is defined for general objects also. So there is you can define it for convex object, you can have axis parallel cut, non-axis parallel cut, all. So it is studied. So there is a classical paper by Park and Tardosh called Cutting Glasses. In that paper, they study a lot of different types of objects. But in this case, we are studying about independent rectangles. So the connecting problem becomes this Park-Tardosh problem for rectangles, and also for other objects like squares or disk, etc. This Park-Tardosh conjecture is kind of settled. We know we can separate constant fraction of rectangles, but for these rectangles, it's not known. There's a huge gap between 2 and log n plus 1. Yeah. So what we'll show later that there's a dynamic program which will return the optimal guillotine separable set in order n to the power 5 times. So it's polynomial time algorithm. So then the solution that we're returning R prime, that is at least more than opt by alpha, because already opt by alpha was a guillotine separable set. So that in turn give you this alpha approximation algorithm for MISR. So this was the optimal solution, but maybe, so this already shows there is a guillotine separable set which is like this 3, but maybe there's another solution which looks like, I don't know, this, which is also guillotine separable, and it will return this solution. Fine. So this is the connection between guillotine and MISR. If we have this existential property that there is a good guillotine separable solution, we can find it efficiently, and that could be a good proxy for the optimal solution of MISR. So is this connection clear? Any question about this connection? Because we'll build on this connection. And the point to notice here is existential. I don't need really algorithmic property here, because this algorithm will return actually the best guillotine separable solution. So that is ensured. So I just need a structural property that actually they are close enough. Guillotine separable solutions are good approximation of MISR solution. Okay, so let me tell you what is the DP, and the DP is basically the same as, I mean, the kind of extension of the previous DP that we studied yesterday for weighted intervals. So we can assume that all the rectangles have some integral coordinates in 0 to 2n minus 1. You can just extend both sides of the rectangles, and there are n rectangles, 2n endpoints. You will get 2n cross 2n grid, but this is non-uniform grid. But you can stretch it and make it a uniform grid, and then all the rectangles have coordinates in 0, 1 up to 2n minus 1. And then what we do is we create this DP, and in the DP there is a table. So DPC stores the optimal guillotine separable set for MISR for a rectangular region C. So in the beginning, C is the whole square. And the base case is if C coincides with the rectangle, we give that to be the solution. So in this case, if this rectangle coincides, this region, red region coincides with the rectangle, we return that to be the solution. And if it contains no rectangle like this, we return empty set as the solution. That's a simple base case. And for the recursion, what we do, the recurrence relationship is you divide this C into by a guillotine cut into two sets, C1 and C2, and there are many guillotine cuts. So one is this, maybe other one is this, and so on. But number of possible such guillotine cuts is only 2n, because if you see, we only have a different structure when some rectangle ends or begins, and there are only 2n possible endpoints of rectangles. So there are 2n possible cuts that we have to deal with. And then for each of these cuts, let's say this is the cut, then I delete this rectangle because it's intersected by the cut, and also this and this. And then I recursively solve C1, this part, and C2, this part. And I do it for all possible such cuts, like 2n possible cuts on vertical side and 2n possible cuts also horizontal side. You can also consider those cuts and return the best one. So DPC is DPC1 union DPC2, where the cardinality of DPC1 plus DPC2 is maximum among all partitions of C1 union C2. All partitions of C1 and C2 of C. So what is the size of this table? As I said, there are 4n possible cuts only, order n possible cuts. How many DP cells are there? So DP cells are also defined by the endpoints of rectangles, because that is the interesting point. So each of the, this is rectangular region. So each of these sides have 2n possible choices. So 2n, 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 n to the power 4, order n to the power 4 possible choices. The number of DP cells is order n to the power 4, and that gives you n to the power 5 algorithm. So is this part clear? Why this DP works? It's just similar to what we did yesterday. The only difference, so there was order n possible cuts in the interval case. Here also it's the same. There we looked into the interval, and the interval had order n square possible choices. Now we have rectangular region, so it has n to the power 4 possible choices. Okay.
So why it is n to the power 4?
Yeah. So as I mentioned, this DP cell C, C is a rectangular region. So let's say, so when we are going bottom up, let's say, so there is a rectangular region C that we want to compute. Now, how many possible choices of C can be there? So this top side, it can have 2n possible coordinates, because as I mentioned, there are n rectangle, there are 2n possible endpoints. So only those places are interesting for any region. Other regions are kind of, will have same kind of structure. So this 2n number of possible top endpoints, 2n number of possible bottom endpoints, 2n right endpoints, and 2n left endpoints. Total, you have 2n to the power 4 possible choices, which is order n. So that's a crucial point. I mean, if we have 4 sides, you see here we have to do 2n to the power 4 possible choices. If we have the cell with, let's say, t number of axis parallel segment, let's say instead of square, I have something like this kind of an object which has t sides. Then instead of 4, it will become t. And similarly, if I have different types of cuts, instead of straight line cut, if I have some cut like this, then that will have again 2n choices, 2n choices, 2n choices. So instead of order n possible cuts, you will have n to the power 3 possible cuts. But for this example, as we have only guillotine cuts, which is straight line cut, we have only order n possible cuts. And if you're, as we are only considering rectangles, we have only order n to the power 4 DP cells. So in total, this is giving us n to the power 5 algorithm. Okay. Any question?
So just to so just to check. So I mean, so this really extends to the case where you have 3 dimensions rather than 2 dimensions, right? And it also works in the weighted case, same thing.
Yeah, this actually works for the weighted case as well, and you can extend it to multiple other dimensions as well. But the runtime would be more because it will become hyperplane instead of straight line.
Right. Yeah. Okay. Thanks.
That will work.
Hello. Instead of this vertical line, while you are sort of taking this orthogonal line, if in that case, is the number of DP cell reduces, or this is DP cells? Like if you are sort of taking the vertical line, then it is sort of n to the power 4 because of these 2n on each side. And now, while you are sort of going for this this orthogonal sweep line sort of thing. So in that case, is this number of DP cell reduces or it remains the same?
Number of DP cells increases because I'll actually talk about that in the next slide, because the DP cell depends on the number of sites. Now, if I take this kind of a cut, then the DP cell will have this complicated kind of shape, which don't have 4 sides, but it has more and more sides. So if you have more sides, then the complexity of DP cell will increase.
Okay.
I will talk about this in the next slide, but this is the first. Okay, just let's think about the guillotine case and understand why it's n to the power 5. If that is true, then we can go to the next step when we'll talk about more complicated polygons and more complicated cuts. But is this part fine? N to the power 5 part?
Yes. Thank you.
Fine. So now we'll go for the more complicated objects. Now the question is, we know that guillotine separability, this alpha factor, is at least 2, but the based on bound is log n plus 1, and we don't know how to improve it. So the question is, as you see in this case, we have this binary tree, and when we cut by guillotine cuts, we get 4 sides again, and we continue and so on. So can we generalize this? So one idea is, instead of this binary tree, we can go for KRE tree. We can have more partitions, and instead of rectangular region, we can probably have complicated orthogonal polygons. And as you see, the DP idea that we mentioned, that actually can be extended to this setting as long as both K and T are integers. So the reason we are going for this is, if we look at guillotine cuts, that kind of restrictive. For example, the example that we talked about, this 4 rectangles. If I have guillotine cuts, you cannot separate out all the rectangles. But if I give you some more flexibility, that I can actually cut something like this and then bend like this and then like this, then actually you're not cutting any rectangle. So you can actually bypass some rectangle along its boundary and then go. So allowing more complicated cuts is beneficial. Then probably you will get more. And second option is, instead of having only 2 cuts, maybe you can have more complicated cuts. So think of maybe the starting object was something like this, and then I can have this red cut, which divides the object into 1, 2, 3, 4, 5 region. So as long as all these smaller objects have bounded complexity, let's say 10 sides or 20 sides, some constant number of sides, and the cuts also have, the number of regions that you get is also constant, I claim the DP will work, and I'll still get the best such separable sets in polynomial time. And that is the idea based on which we'll go. And we'll show first a 6 approximation, for which we'll use a tripartition, and the number of sides will be around 26. And building on that, we'll show a 2 plus epsilon approximation, where K is equal to actually 2 and T equal to something. We talk about the DP table now. So why it is true? Now we talk about some KRE partition into T-sided polygons. Think of the
can you please switch off their
yeah, there is some noise. Suvendu Saha, I think you have to mute yourself.
I'm trying to mute.
Anyway. So so why this DP table works when you have KRE partition into T-sided polygons. This is one example. So let's say some complicated polygon is there that we are dealing with, which has T sides, and now we can show if we can show that there is a partition of this object into 3 regions by this yellow cut. And let's say this yellow cut has, it divides into 3 regions, and it could be even K actually. So in this case, K equal to 3. So C1 is one region, C2 is other region, and CK is another region. So there are 3 regions, and each of these regions has at most T sides. Then why this DP works? Because then again, for the DP cell, we look at how many possible candidate polygons are there. We are looking for only polygons which has T sides, and each of these sides can have 2n possible candidates. There are, I mean, if it has T possible sides, there are T by 2 vertical and T by 2 horizontal sides, and each of these vertical sides have 2n number of possible candidates. Horizontal sides have 2n number of possible candidates. So total number of possible orthogonal polygons which has T number of sides is 2n to the power T. So in the last case, when we have T equal to 4, then it was 2n to the power 4 or order n to the power 4 for the guillotine setting. And if we have KRE partition, so there are K regions that you are getting, then this complicated cut, what is the complexity of this cut? So as we know, there are K regions, the total number of sides of all these K regions is at most KT, but each of this cut edge is shared by at least 2 of these regions. So KT by 2 is the complexity of the cut. So in the guillotine setting, it was only one cut like this, or other cut was like this. So there were 2n possible choices, 2n plus 2n, 4n possible choices. But now for this complicated cut, it has KT by 2 possible sides. So you can have n to the power KT by 2, 2n to the power KT by 2 possible cuts. And then the DP will work as the previous case. So what you'll do is you'll start with an initial object, and then you try out all possible cuts of size KT by 2. By size, I mean the number of sides in the cut is KT by 2, which divides the polygon into a K number of regions. And then you recursively call this DP process in the smaller cells and continue. And as long as K and T are constant, this DP will still run in polynomial time.
I think don't you need to show something about smaller regions as well? I mean, if they are very high complexity, then you may not be able to.
Right. So that's what we have to ensure. The smaller regions, the complexity does not grow up. So for example, I want to maintain always the sites, this complexity of the region remains T. That's one of the challenges. So for example, I can probably give, yeah. So for example, I can give you one example. So let's say I allow not guillotine cuts, but let's say some kind of L kind of cuts. So one kind of problem can happen is, let's say I start with this object, and then I cut like this L. Then the next object I cut like this L, and then I cut like this L and this L and continue. In that case, this region, its complexity increases. It may not remain constant. If you have this L kind of cuts many times, order n times, then the complexity of the region will become order n. By complexity, I mean number of sides of this region, because now it is 1, 2, 3, 4, and it goes on like this. It becomes too complicated. So we have to ensure the property that we start with the optimal some region, and then we divide into the smaller polygons, but we still maintain the complexity of the regions don't grow. So it will still remain, let's say, 26. That is the challenging part. We have to find such a partition. Otherwise, it will not work. And in guillotine case, it was very simple because you will never increase the complexity. It's just end-to-end cut, so it always remains 4. But when you have bends, it can increase. So we have to ensure to find some way, some kind of possible cuts which does not increase the complexity of the region, the number of sides in the region. That's one of the crucial points that we have to ensure.
Okay, thanks.
Any question? There is some question on this. Is the claim that every small part is of size KT by 2? No. So my claim is every small part has side length at most T. KT by 2 I am claiming is the complexity of this cut. So let me use some other color. So this, I am saying that, okay, the C1 region is this region, and this region, it has at most T number of sides. Similarly, C2 has T number of sides. C3 has T number of sides. And if I look at the cut, which is, let's say, this yellow region, this cut, total number of sides that we have in the cut is kt by 2. And that is coming from the fact that there are k regions, each has t number of sides. Total number of sides can be kt, and the cut for each of these edges, it is shared by 2 of the regions. So you can have at most kt by 2 number of sides. It can be actually less than this value, but a rough estimate is fine. The main point is, as long as k and t are constant, this remains constant, this kt by 2. So assuming this property is true, that I ensure some cutting strategy such that all these smaller polygons remain constant complexity. So number of sides of the smaller polygons remains, let's say 26 or 1000, some constant value. And I ensure that the cut also has constant complexity. It has, let's say, 20 number of sides. Then I want to claim the DP will work. So is that fine? Is that claim, or any question regarding that? Because the number of DP cells, it only depends on the number of sides in these smaller regions, and they are constant, so it's n to the power constant, n to the power t. And the number of regions that we have k, it ensures it's constant, so it ensures the number of edges in the cut is also constant, and that ensures the number of possible choices that you have to iterate over in each of these DP step is also constant. So totally you have n to the power constant possible choices, and that gives you a polynomial size DP. So does the cut always have to be monotone? Yeah, that's a good question. Actually, for our algorithm, the fixed approximation it is monotone, but we can show for the 2+ epsilon it's not required to be monotone. So by monotone it means the cut can be it may not be something like it may not be something like this always, but it can be some weird shape like this as well. So that we'll go over. But for now, assume that this property is true, then the DP will find it. So then the next question is, how do we ensure this property? How do we ensure that the cut, we can always define cut such that the complexity does not increase? And then how do we ensure that, okay, even if it is true, what is the guarantee that we don't cut too many rectangles? So those are more crucial part. But for now, I think this is kind of simple to understand, that if we have this property, that there is some sequence of cutting, recursive subdivision or cutting, such that each of these regions have constant complexity and there are constant number of regions, then the DP will find it. That's the thing you can assume for now. Okay. Fine. So now let's look at the recursive partitioning. And as I mentioned, that from the previous previous algorithm, what we showed is, if we have k and t to be constant, number of partitions and number of sides in per region is constant, then DP will find it. But question is, how do we find such partition? And there were two ideas here. First, we show the cutting strategy, which uses something called fence and cutting. And then you have to show the analysis, that why it is ensuring that not many rectangles are cut by this, and that will be using some nesting and token counting argument. Okay, so to show this first part, that there is some cutting strategy, first we'll assume that the optimal solution that we consider, it is maximal. So maybe this is the optimal solution, but then we can enlarge it a bit, so grow such that the new rectangles are kind of larger or a superset of the previous rectangle, and we only work on the separability of these rectangles. And if we know that there is a cutting sequence which separates a good fraction of rectangles of this type, as these rectangles are superset, it also separates out a good fraction of rectangles of the optimal set as well. So from now on, we will assume the optimal solution looks like this. It's a maximal solution. So from now on, we'll assume that we are given, let's say, the maximal optimal solution, and then we'll try to process this solution and show there is a good quality solution which has this recursive partitioning property, because then the DP will solve. So this DP was the algorithm. That is the algorithm for our problem. Now this part is showing us existential property. So it need not be algorithm. It can be just constructed. Okay. So what is the strategy? So first of all, if I have this kind of a rectangular arrangement, and if we find some cut, if the cut is in the boundary, then it's kind of lost, because you lose all the rectangles that are cut, but you don't really make any progress because you lost those rectangles and you did not really make progress. So divide and conquer kind of once you have two smaller regions which are kind of balanced, and then you make some progress. So maybe it's better to have cuts which are not near the boundary. So we want to block or protect the boundary rectangles using something called fence. So if some rectangles are touching boundary or close to boundary, we'll create these fences which basically lies on the top of the rectangles. So on left side, this red fences are there, and right side there are blue fences which are there. And then, so basically fences are horizontal line segment that join boundary of a piece to the boundary of a rectangle without intersecting any rectangle. So you can think of a ray is being shooted here. So the ray shooting is done here, and then it is hitting this rectangle, and this is the fence that we get. So if it hits a rectangle, then you stop. And yeah, if a rectangle is having a fence on one of its sides, we call it's protected, or it's a boundary rectangle. So these rectangles, these boundary rectangles, we'll try to protect. We'll not cut them, and then maybe we find some cut. So the goal is I don't want to cut through the fences. So this kind of cut is not allowed. Fences will not be touched. They are protected. These boundary rectangles. This is not allowed. It's a violates property 1. And I also ensure that the horizontal segments of cut do not intersect in rectangles. This kind of cuts is also violating because this horizontal part is intersecting rectangle. So we'll only look into this kind of a cut where the horizontal part is not intersecting any rectangle. It is going along the sides. Only the vertical part can intersect rectangles. Like this. So we cut like this, and then probably we got this boundary rectangles, and we create the fences. Then again we got another cut and create fences, and we continue. But now in this region we cannot really cut again because whatever we cut, we have to cut a fence if we just create a vertical line. So what we'll do is we'll use bends now. So the bending might be done like here, and then you get this region, and again you use a bend and cut like this, that kind of cut, and you get this and continue. So that will be our strategy. So intuitively, the idea is I want to start a cut from a bend, from a fence. So this is a fence. This is also a fence. So I want to start a cut along a horizontal line, which is a fence. And I want to exit the polygon also along a horizontal line, which is a fence. And I want to go vertically between these two. That's a high level idea, and we'll show why it works. Okay. So the partition rule will be something like this. So we will have some fences, and from some fence, we'll select the fence in some according to some rule. We'll shoot a ray on top and bottom, and if it hits some other fence or other rectangle, other fence actually, or a protected rectangle, then we actually go along that particular line and we exit, and that will give us this region. So one region is this, other region is this, and third region is this. And the invariant we'll maintain is this pieces will maintain to be horizontally convex. That means that if I take any 2 points, let's say it looks like this, any 2 points, draw a horizontal line that will remain within the polygon. So it is not a convex polygon, but it's horizontally convex polygon, and will ensure that this polygon's complexity or number of sides is constant. Okay. So now let's go into more detail what's being done. So we define fences again more formally. So for each point on the boundary of the left vertical edge of a piece, we shoot a horizontal ray towards right till it hits a rectangle. So in this case, we are shooting the ray and it hits here, so we stop here. Here we shoot the ray and it hits here and stop here. So these are creating some fences. And whatever rectangle top side is contained in the fence, we call it protected. So we will not cut those rectangles. That's our invariant we'll maintain. So in this case, this is protected, this is protected, this is protected, and so on, because their top side, one of the sides are completely contained within this fence. And similarly, we do fencing from right side as well, and there we shoot the ray to the left. Okay. Okay, so now let me prove this line partitioning lemma, which will ensure that we can find a cut such that the complexity does not go up. So in this case, we'll show, okay, there is given a horizontally convex polygon which has 26 sides. We can find a cut C, and C is this yellow region, basically that cut, which has at most 8 line segments, which is constant. The cut has constant complexity. C divides P into constant number of polygons, 3 number of polygons, and each with at most 26 sides, and each are actually horizontally convex again. So K equal to 3, and again P equal to 26, it remains. And the cut has special property. It has only one vertical segment, and that can intersect some rectangles. So maybe this particular region, there are some rectangles that are intersected, but none of these rectangles are protected. So if it has fence, we don't intersect it. Otherwise, we can intersect. That is fine. We have to kill some rectangles. Only this vertical line will kill some rectangles, and the horizontal line segments will not cut any rectangles. So L does not intersect any protected rectangles. So L does not cross any fence. This is the lemma that we'll prove, and that will kind of ensure the property that the constant complexity and K and T are constant. So you can actually find this kind of a cutting sequence using DP, but then we have to show it's also good. So the analysis will be showing that it does not cut too many rectangles. But for now, let me just prove this fact that this property is true. So what we do is, we know that the P has at most 26 edges. That's the assumption we start with. So in the beginning, we have only 4 edges, but as we cut, things can, the complexity can increase, but we'll ensure it will never go beyond 26. So if you have 26 number of edges, then there are at most 13 vertical edges. So there are V by 2 number of left vertical edges, which is, let's say in this case, 7. As you see, E1, E2, E3, E4, E5, E6, E7. There are 7 vertical edges, left vertical edges. And we divide this into 3 regions, ET, E3, EV. And they're kind of equally balanced. The middle portion has like slightly more maybe. So these two are V by 6 floor, and this is V by 6 ceiling. So we got these 3 regions. And now from this EM region, we look at all possible fences that are getting out. So maybe the fences will look like this. There are many fences that are going out. We take the fence which has rightmost endpoint. So in this particular case, this F is the endpoint. F is the fence which has rightmost endpoint. And from this endpoint, we shoot a vertical ray to the top and bottom till it hits a protected rectangle. So RT or RB is hit. If it hits, then we take this bend and we exit along that fence. Because RT was a protected rectangle, it's already has a fence here. So we just go along this and exit. So this is the cut that we are getting. So from this, we go like this, and then this. This is the cut we are getting. So we have to ensure these 4 properties that I mentioned. And in this particular case, the 3 properties are kind of easy to check. First is C has only 8 line segments. It has constant complexity. The cut has because we have one vertical segment, one edge here, F. Then the second one is here, 2, then 3, then 4, then 5, and here it is 6 and 7 and 8. So the cut is of constant complexity. That is fine. There is only one line segment that can intersect some rectangles, and that is also true because only this is the line segment which can intersect some rectangles. Because this is just bypassing the rectangles, the fence. This is also a fence, and it's also a fence. So all the remaining 7 sides are fences. Only one side is a vertical line segment which can intersect some rectangles. So third property is also true. And as you see that that L by definition, what we do is we are shooting this ray till it hits some protected rectangle, and then we take this bend. So it does not intersect any protected rectangle. That's also true. It does not cross any fence. So first, third, and fourth properties are true. Now the last property, you have to ensure that the complexity also does not grow up. So in this case, we have to ensure that this cut complexity remains 26. So the reason it will not grow, intuitively what we did was we divided this vertical sides into 3 regions, ET, EM, and EV. Now if we look at the longest, we look at the fence which has the rightmost endpoint, and then we shoot the ray to the top and bottom. So that ensure that you will not hit any fences from this red region EM. You can hit fences from the top portion or the bottom portion, but at least you will not hit anything from EM side. So now what happens is when we create this new region, the complexity of this region C1, it has some new sites. So you're adding 1, 2, 3, 4, 5 new sites. But we have to ensure that actually in the beginning piece we have 26 sites. We have to remove some of the sites so that we can support this newly added sites, and that is made sure because if I look at C1, it is disjoint from this set EV, and we made sure EV has sufficient number of edges, like V by 3 number of edges or V by 6 number of edges. In this case, it is roughly 5. And also, if I look at C2, then again it is disjoint from this ET edges, and if I look at this C3, it is disjoint from EM number of edges, EM edges. So that is ensuring that okay, by this cut we are increasing the complexity because some new edges are being added, but also the region that we are getting, it is not having a lot of edges which was there originally in the piece. So we are also decreasing the complexity there, and that is making sure the complexity does not grow up. So for example, if I look at C1, this region, what is the number of sites it has? Initially, the whole region had V number of sites, but now I know that okay, at least number of vertical sites was V, and at least I know this is deleted. V by 6 number of sites are no more there in C1 because they are not part of C1. So that is minus, and we're adding 2 new vertical sites. One is 2, other one is 4. So plus 2, and you can show this is actually less than 13. And 13 was the bound that we need. That it is at most 26 sites, at most 13 number of vertical sites. Similarly, you can show it for other sites as well. So this ensures that you have constant complexity. Any question?
So in this picture, is it possible that the fence F continues until the right side boundary?
Yes, actually that is possible. So that's even better. So that's a guillotine cut. So fence will continue and
that's right. Okay, yeah. Sure, yeah.
So that in that case, yeah, there can be fences. If you have guillotine cuts, the fences can go from one boundary point to other boundary point, and that's actually better for us. So this is a more harder case because the fence is blocked. Okay, fine. So now we have this constant complexity part as well, and we know what is the cutting strategy. So final part, we have to show that actually this is good cutting strategy. We don't cut too many rectangles. So recursive partitioning look like this. So you start with some objects, and then you first cut like this, and then cut like this, and cut like this, and so on. Continue. Now we have to show that we don't need too many rectangles. So for each filled rectangle, you can actually save sufficient number of rectangles. And each filled rectangle that is not horizontally nested. Okay, so we'll define something called nesting and use some kind of charging argument to ensure that. So let me define this nesting relationship, which will be useful for the analysis. So now we are only in the analysis part. The algorithm was TP, which we did. The cutting strategy, which is essential, we showed in the previous part. And now we only focus on the proof of the approximation guarantee. So first we define a rectangle to be vertically nested or blue if its top or bottom edge is contained in the interior of some other edge or boundary edge. So for example, if I take this edge, its bottom edge is contained within the boundary edge. So we call it nested vertically. Similarly, if we take another edge, let's say this edge, its bottom edge is contained within some other rectangle's boundary edge, interior of some other rectangle. So in this case, it's a vertical nested rectangle. Similarly, we can define horizontal nested. This is a horizontal nested rectangle, or it is red. In this case, this particular edge is contained in the interior of some other edge of some other rectangle. Now, one observation is a rectangle cannot be both red and blue. So, and if it is not red or blue, we call it gray. So why? So let's say this is vertical nested, this is horizontal nested. As you see, if something is vertical nested, you have some extra space here. And if you have it horizontal nested as well, then you need some rectangle which is like this, and that cannot be true. So a rectangle is either vertical nested or horizontal nested, or it may not be nested at all, which is this kind of a gray rectangle, which is neither. So this is kind of a partition of the rectangle, and I will assume that the number of red rectangle is small, so less than half. And non-horizontal rectangle, nested rectangle, which is either blue or green, they are more than half. Okay. Now we define something called seeing, which we'll use basically for charging. So we call a rectangle sees another rectangle, sees the corner of another rectangle. So let's say R is a rectangle. It sees another rectangle R prime. R prime's corner, top left corner, let's say C. If we join this corner with by a horizontal line to this particular rectangle, and this does not intersect any rectangle in R, it does not contain top edge of any rectangle, and it is not the bottom right corner of rectangle of the rectangle R. Then we call it C. So for example, if I look at a particular corner point, then it is not visible, because if I join this corner point with this, then this is containing the top edge of another rectangle. This is not visible. So think of you are here and you're looking from this place, and you can only see horizontally. What is the first point that you hit? That is the rectangle that you can see. Similarly, this region also you cannot see, because if I join this and this, it is intersected by another rectangle. It's blocked by a rectangle. You cannot see. And third point is here. If I have here, it's kind of a below point. So if I look at any interior point of the rectangle R, it cannot see this point horizontally. So this is the definition of seeing. You can just assume that, okay, if from I take a rectangle, I take a rectangle, I take a corner, and if I join them, and if it does not intersect any rectangle, or it does not contain rectangle, can you mute yourself?
Excuse me, once again, Arindam, please mute yourself. Shubhendu, I think you need to mute yourself. Okay.
Okay. So that is the definition of seeing. Okay.
Excuse me, can everyone mute themselves except the speaker?
I'm
trying to mute him, but I'm not able to mute him also.
Anyway, so the point is, this definition of this seeing, it ensures that if I have some horizontally nested rectangle, the red rectangle, then it does not see any corner in the nested side, because the whole region in the right side is completely blocked by another rectangle. So red rectangles, we cannot really see any corners. But what will ensure, if a rectangle is vertically nested or gray, then it sees at least one of the corners on each side, and that will be helpful in the token distribution. We will actually distribute token of killed rectangle to the rectangles that it can see. Okay. So the seeing definition is clear. I mean, it's just saying that if I take a corner, I take a horizontal line joining the corner and the particular rectangle, it should be the first rectangle. There shouldn't be any rectangle in between them, touching that particular line. Okay, so now the claim is, if some rectangle is not horizontally nested, it can see at least one corner on each side, or it is already protected. So I have 10 more minutes. So let's say what we do is we take one rectangle R and it is not horizontally nested. So what we'll do is we extend its top edge till it hits the boundary point. And if there is, it already hits boundary point, then it's already protected by definition of fence. So there should be some other rectangle which is blocking it. So this is the first such rectangle. Now there can be two cases. One case is that rectangle's y coordinate is same as R's y coordinate. The top edge kind of lies in the same vertical line, horizontal line. So in that case, we are fine, because then this corner is seen by the rectangle and this corner is seen by the rectangle. Whether R prime has the bottom edge above or below R, both the cases we are fine. So let's take the other case when it is not the case that this is lying on the same horizontal line, but they can be above or above. Basically, this is blocked. This line is blocked by this rectangle. So then, first of all, we assume this is not horizontally nested. So this kind of a situation will not occur. That R is is completely blocked by R prime because it's not horizontally nested by definition. But then there can be two cases that, okay, this two rectangles R and R prime, they are touching each other or not. If they touch each other like this, we can show this corner is visible. And if they don't touch, then we can show using the property of maximality that the only possible case which can happen is this case. But then again, we have one corner which it can see. So that's the high level idea. I will not go to the proof, but it's not too long either. But I have less time, so I will not go over the proof. But the point is, if it is not horizontally nested, it can see one corner on each side. So charging argument is this, that if some rectangle is not horizontally nested and intersected by L, then for the rectangle we have charge 1, we distribute half charge to the corner to the left and half to the right. So there are these two claims which will give you the 6 approximation proof. The first claim says that a rectangle R prime receives a charge to at least one of its corner. If it happens, then it is protected. So think of this case. This rectangle. So it is receiving some charge. Maybe this corner is receiving charge. Why is it receiving the charge? Because some rectangle was killed, and that rectangle could see this particular rectangle. And that's why this killed rectangle, let's call it 1, this is 2. So 1 was distributing half charge here and maybe half charge here. So this corner got charge from this. So as it got the charge, this was actually the first rectangle that was visible from the rectangle 1. So that's why it got the charge. So once we kill the rectangle 1, now we create this rectangle 2 is actually visible from the boundary, or it is becoming a part of this fence. And once you get a fence, it becomes protected. So if a rectangle gets a charge, it becomes protected. And that's what we want. So basically, we'll ensure that there are many rectangles which will receive the charge. And that means there are many rectangles which will be protected by fence. That is good for us. And then also we'll show that the corner of rectangles are not charged many times. So if a rectangle gets charged once, it will not, the same corner will not get charged anytime further. The reason is when we get the charge, we get the charge when some rectangle which was just next to it was cut, and this is the first rectangle which was visible from the fence, and it gets a charge. So the first time it gets there and then it gets protected. So next time onwards, it cannot get any charge because there is no more rectangles which can be there for which this property is true. So each corner will get charged at most once. And this gives you the 6 approximation. So this claim 2 and claim 3 we assume. And then the proof is, okay, first we lose a factor 2 because we remove all the horizontal nested rectangles, and only we consider the rectangles that are not horizontally nested. And we assume the number of horizontal nested rectangles at most half. So we lose at most a factor half. And now for the remaining rectangles, so basically we are cutting some non-horizontal nested rectangles and we are distributing the tokens of these rectangles. And what we showed is any rectangle is receiving, each of the corners is receiving at most once charge. There are 4 corners, so you'll receive 4 charges, and each of them has half token. So at most 2 amount of charge is received by each of these rectangles. And once they receive, they are protected. So if we have k number of not horizontal nested rectangles that are cut by vertical lines, and if they save t number of rectangles, then we have the property that t is at least k by 2. From the fact that totally k are killed, so you're distributing k tokens, and each of these rectangles which are receiving token, they can receive at most 2 tokens. So at most k by 2 rectangles, you have to save at least k by 2 rectangles. And that ensures this t by k plus t is 1/3, and that ensures the total loss to be half times 1/3, which is 1/6. Any questions so far? So now we build on this idea of, again, charge distribution further and further. So for example, if I just look at this proof, the loss we had was this factor 2, which was half times 4. So if I have some modified proof for which this property was true, that instead of 4 corners, only 2 corners are charged, then everything will work out as previously, but instead of 4 here, I'll have 2 here, and that will give you 1, and that will give you a factor 1/4 by the same argument. So how to ensure this property that only 2 corners of a rectangle are charged, not 4 corners? So for that, what we do is we get fences which are more complicated, which has more bends. The reason being, if we look at, let's say, this particular rectangle. Now it can, when this was killed, maybe it will get charged from here, and maybe for some other rectangle was killed for which it could have gotten charged even in this corner. But then again, if this was killed like this, it could have gotten charges from here as well. So you want to ensure that if some rectangle is protected, it should not get charged from the other side. So the longer side is making sure this rectangle is also protected by using more bends. So now the fence is like this bends, and you protect more rectangles. The right side is also blocked. You cannot get charged from the right side. You can only get charged from the left side. So only 2 of the corners will get the token, not 4 corners, and that will give you this 4 approximation. Okay. So we build on this again. So now the idea is we want to save as many rectangles as possible. So whenever we are giving token to a rectangle, we want to ensure that it's safe. So let's say in the good case, each rectangle can see. So we proved that each rectangle can see at least 1 rectangle on each of the sides, and that was giving us this 4 approximation. But if, for example, if we know that each rectangle was seeing 2 rectangles on each side, then it is even better. So then, for example, in the one case when there are 2 corners which were seen by the rectangle, then after killing R, actually both this will be protected. So we are actually in the better shape. So, so having more corners visible is actually better. So using, but it may not be the case always it is true. For example, in this example, for example, it only sees 1 corner, not 2 corners. But then what we do is we still have 2. Now we have, earlier we had 1 token and we're distributing half and half. Now we create 4 tokens, each of size 1/4 for a rectangle, and we distribute 2 tokens to right, 2 tokens to left. And we have something called indirect C. So we distribute the first token to the first directly visible corner, and the second token we kind of pass it along, and we actually go along this line, and the last rectangle hits, and if this last rectangle becomes a red rectangle, we pass it to this, and if it's not a red rectangle, we pass to the other corner. So it's technical, but what we ensure that you can actually ensure that you can distribute 2 tokens for 4 tokens, basically 2 to each side, and you will make sure that whatever rectangles are getting token, they are protected. We will not kill them by fences. So that gives you 3 approximation, because now in the previous proof where we had only half times 2, we'll have now 1/4 times 2, which is half, and that will give this bound to be 2/3, and that will give here 1/3. So that gives you 3 approximation. Now from 3 to 2, it's slightly more complicated, but it is based on the token distribution idea only. Now instead of 2, actually we distribute more and more tokens. So it has a more complicated token distribution strategy, and also now we need more additional properties in this partitioning lemma. The previous partitioning lemma we talked about, which has 20 sides and other stuff, that has only the fence was only 1 line segment. But now what we'll do is we'll ensure the fences have more sides, so 1 by epsilon number of sides, and that will need these polygons also to have more complicated number of sides, so maybe 1 by epsilon to the power constant, but it's still a constant, and it may not be even horizontally convex, so it can look this kind of weird shape as well. So that's possible. And what now we ensure that whatever rectangle we kill, we can distribute more and more tokens. So now this is what we do is we create some kind of directed graph, and we ensure we create some kind of a tree basically, and we ensure that for a cut rectangle, if we take the path from this, either we hit a red rectangle or we hit sufficient number of blue rectangle, at least let's say 1 by epsilon number of blue rectangles, and we can protect them by fences of size 1 by epsilon and then stop. So this will ensure that for each of the killed rectangle, blue rectangle, either there is a corresponding saved red rectangle or we save 1 by epsilon number of blue rectangle. So intuitively that gives you 2 plus epsilon approximation. So almost all the blue rectangles are saved, or if you kill some lot of blue rectangles, equal number of red rectangles are saved. So that gives you 2 plus epsilon approximation. So any questions so far? Yeah, this last part was technical, but the idea builds on the previous fact that as long as we have some cutting strategy which ensures we have constant number of sides and there are constant partitions, and then this token counting argument says that for each cut rectangle there is a good number of saved rectangle that ensures this guarantee. So key takeaway is the idea of fence and cutting strategy for the geometric decomposition, which might be useful in other problems, and this token distribution strategy, which might be used in the analysis. Yeah, Sujay, you have a question?
Thanks, Arindam, for the nice talk. Actually, I have a question. So we know that there exists
Yes.
a p-test for this problem. I mean, we don't know the answer, but because there is a q p-test, we know that this is not APX hard. So what is the problem precisely with this strategy? I mean, why it cannot be pushed to 1 plus epsilon?
Okay, so this is a tight example for this problem. Actually, you can, I mean, the way we do the analysis, we are losing half of the rectangles in the beginning. We are only taking red or blue. So in this case, actually, we lose half. In fact, the problem is this charging argument that we are doing, or token distribution. It uses the idea of seeing, which works for rectangles. But if you just have, let's say, axis parallel line segments, so similar kind of thing, let's say like this. So even in that case, we don't know how to beat factor 2, because this kind of charging ideas will not work, or none of the strategies even work for line segments. Forget about rectangle. So there is already this problem with line segments. I think to go beyond 2, we need some significantly new techniques. At least first we have to understand the line segment, axis parallel line segments, how to resolve them.
But line segment 2 approximation is very trivial, right? It's just 2-dimensional.
That is the best known. So can you get better than 2? Even 1.99, that is not known. And it does not seem like it's easy.
And one additional question. So this strategy will work fine, I guess, also if you have a constant number of orientations. So this is like only 2 orientation.
Okay. That actually, I mean, the DP one will work for sure, but the problem could be with the charging argument. I have to think a bit. Yeah, charging, I'm not sure, but maybe it will work. I mean,
if you have constant number of orientations, then like this cut line, so of course, it's no longer orthogonal cut, but this cut also has like only constant number of orientations.
Right, so, as I said, the cutting strategy will work, but the analysis part, the token distribution strategy that we have, it needs some more work. It's not clear. So analysis part we have to work out, but the DP will work, the cutting strategy will work. Those two are fine. But whether those cutting strategies produce good cut or not, that analysis part, it needs some more work.
Okay, thanks.
So I have around 5 minutes more, I guess. So I will just briefly talk about the weighted case. So this does not actually, our technique does not extend to the weighted case, because we crucially use this token distribution idea, which relies on seeing, and it uses the cardinality kind of properties in the analysis. So for this, still the best known approximation is order log n. But I believe our algorithm should give you constant approximation as well, but I don't know the analysis. So we don't know how to do the analysis. So my conjecture is probably even the guillotine cut will give you 2 approximation for MISR, but we don't know the analysis, how to do it. So briefly, this log n algorithm, it uses a linear program, which is called click constraint LP. So it says that, okay, I create this, I look at the intersection graph, and this says that I want to select maximum weight independent set, xi is one independent set, and for each of the, so xi is the selected rectangles, and for each click, I want at most 1 rectangle to be selected. And that will ensure the independent set property. And this LP has connections with graph theory, and integrity gap of this LP has connection with other problems as well. So this is a conjecture actually, which says chromatic number and click number of rectangle intersection graph are constant factor array. If that conjecture is true, it's an existential conjecture, then using this LP, you can actually get constant approximation for weighted MISR. So that's a structural problem for graph theorists. Prove this fact. That so right now we only know it's order omega log omega, but if you improve to order omega, you already get a constant approximation for MISR. Okay, so to conclude, these are the open problems. The first is, of course, Peters for MISR, which will be very interesting. In fact, people believe there should be a Peters for even arbitrary oriented rectangles or polygons as well, because there is a Q Peters for those objects. Second is even the next easy question, at least to go beyond our technique, you just get 1.99 approximation for axis parallel line segments. And then the question is second, can we extend our techniques to constant approximation for weighted case? So as I mentioned, the algorithm should be fine, the recursive partitioning should be fine. It's only the analysis part which we could not show. Third, fourth is resolution of this conjecture that chi-g, the chromatic number of rectangular intersection graph, is order omega g. Omega is the clique number of the graph. Then the resolution of Cock-Tardos conjecture and extension to higher dimension. So you can show for d dimension, can you get similar kind of bound? And even for arbitrary line segment, when we have arbitrary orientation, the best known bound is n to the power epsilon. Can we get even polylog n approximation? Not poly n, but polylog n approximation for this problem? A constant would be even better, but we know nothing there. So these 7 questions are open problems, interesting open problems in this area. Okay, so I guess that's it. Any other questions?
So the last result uses what? Like separated theorem for string graphs, no? That one.
Yes, yes. Fox and Park, yes. Yeah, actually, I told about arbitrary line segment, but it works for any curve such that each curves intersect with each other constant number of times.
So Arindam, I have a question. Sorry, Arijit, you had a question?
No, please.
Okay. Although this is not really studied typically in an offline setting, but I was just wondering, because this weighted thing seems quite hard and it has been open for long, is there any study on something like a resource augmentation? So let's say I allow you to stretch the rectangles by...
Yeah. Then you can get beta. Right. So there is a result by Parinya, Andreas Vise, and I think Adamasek, where they showed that if you have rectangles and you can either shrink the rectangles. So in both sides, you have whatever length you have, you reduce by 1 minus epsilon factor. Then the structure of the intersection graph becomes much more simplified, and you can get a constant approximation in that case. It was Peters in that case, and this conjecture is true. Then the chi-g of that change graph is within order of omega g of the original graph.
So this is for weighted as well.
I think for weighted as well. That I'm not sure, but I think for weighted as well. But at least for unweighted, for sure. Yeah.
Sure. Okay. Got it. Thanks.
Any Orjita, you are asking some question?
So no, again, we can take the questions offline because we have to set up the next speaker.
Sure.
So thank you, Arindam,
for
the very nice talk, and everyone for attending this.